I can spend time when to Spain in 10 days.
You were in
But now I was thinking about work for a day. There's still this like kept going.
Yeah. Okay. Hello. Let's continue. So basically in this first hour and these first 2 hours, I'm giving you a rough overview of the whole thing, as you might have noticed by now. And we went up to the fact that you record, or we record, or cognitive neuroscientists record EEG data in the setup where you present stimuli, for example, visual stimuli, have things sync between your EEG setup and your presentation. Then you record these sweep, sometimes called traces of EEG, which you then partition or epoch or cut, whatever you want to call it, into these segments, and then you average segments to get what is called an event-related potential. And then this book is called An Introduction to the Event-Related Potential Technique. So these kind of plots that you then get, they make up, they are a research field or a basic research result on their own. And these then come with certain conventions and a certain tradition that we will briefly talk about on the next slide. Have you read event-related potential papers at all? Have you read EEG papers? Yes? I mean, in your other courses, of course. Which of them use event-related? How many? Did some of them use event-related potentials as the results? Yes. Did some of them use frequency analysis as the results? Yeah. Okay. Did they use something else in their results? No. I mean, another option would be to, for example, do dynamic causal modeling of EEG data, or to do independent component analysis of EEG data, and if that is the result. But you can do an event-related paper by then ending up with these kind of plots. So that's a paradigm, that's in terms of scientific paradigm, and it's kind of a result. So for example, the stuff that Stefan currently is writing up is without modeling this further or doing anything, this is a result, it's a research paper. And once you have done something like that, you have at least done something. So there is, maybe you've seen that in talks and maybe you've seen that in papers, there is kind of this tradition of plotting event-related potentials the other way around, so plotting negativity upwards. So that's then here, of course, positivity is plotted upwards like always, but sometimes you have this -5 above here and plus, and then they always tell you, yeah, its negativity is plotted upwards here. It makes no sense, and it has a long tradition somehow in EEG, but I also tried to look up and also look where this is coming from, but it's actually not that easy to figure out where this actually is coming from. So somehow it got into the EEG tradition, but we don't do that, and it's over. And so EEG is like any other quantitative measurement. Positivity is upwards, negativity is downwards. So you sometimes still see that. It's just weird. And Luck agrees, it's not only me. Then you might have heard, and we've seen it here actually, that these peaks, these amplitude excursions, they get names. And part of this course is actually for you to learn the vocabulary of these names and associate them with something, because you will hear people talking about them. And if you want to have a professional conversation with a fellow cognitive neuroscientist, you should, of course, have an established basic vocabulary. And easy thing about them is maybe that positive peaks are referred to as P's, so for positive, negative peaks are referred to as N's, and then there are two different conventions for assigning numbers, and both of them exist, and you find these. You find certain ones in certain literatures and other ones in other literatures. So one is then to name them by their latency or approximate latency, because there's latency variability, of course, for EEG or event-related potential peaks. These are then these things like P100 and 140, which refer to positive peaks 100 milliseconds post-stimulus onset, or negative peaks 140 milliseconds post-stimulus onset, or they are just ordinarily numbered, so P1 for the first positive peak and 2 for the second negative peak, which also means there's an N1. Yeah, so they exist, and certain things, for example, the P100 is usually associated with visually evoked potentials, and then yeah, it pays in discussions and conversations to learn which peaks typically appear in which event-related potentials and at which time, and this is what the event-related potential part of the course will actually do. Yeah. So one thing is, and this is also something to get used to, especially if you're doing EEG research yourself, in papers and yeah, other forms of scientific communication, you will often see what is called a grand average, which just means it's the average of the individual event-related potentials from participants, average over participants. And these grand averages have a tendency to look nice, clear, and like the ones that you see in the textbook. So this is actually the grand average from this paper for which you have the data, where we presented checkerboards with reversal. So there was a checkerboard onset at 0, and then there was a checkerboard reversal when all the white spots went black and the black squares went white at 500, and then the typical response that you get to these checkerboards is the P100, which is this peak here, and of course, well, maybe not of course, but it's stronger for high contrast than for low contrast. So this is the C. Michelson here, high contrast 1, low contrast 0.25. And you see it quite clearly. You see that there's also some variability, and you see that the second response is a lot lower. You should, from these grand average, however, not think that every EEG data set that you record from a participant and then evaluate it individually, or even subsets of these data looks like that. And also your advisor or supervisor should not expect that, which is sometimes annoying, because if you then show your supervisor these kind of data here, for example this participant, then that doesn't really look like the textbook picture or the picture that people see in papers, because in papers usually you see this. But it's just the case that there is between participant variability, and this can have many reasons. Maybe I don't need to zoom here, sorry. So you see that here, in terms of the P100, you see a good peak here, you see a good peak there, you see a good peak there, you see a good peak there, you see a good peak here a little bit, here a little bit, here a little bit. This can have different reasons. Sometimes the case is that you just have an overall quite bad EEG signal because the electrodes are not really attached. Then another thing is, of course, that the anatomy of participants' cortex is also different, which means that if you have a certain electrode that projects the electrical activity in the brain very good to this electrode in this participant, the same electrode might not represent what is going on in another participant good, because although you're trying to put them all on the scalp in a standardized way, which we will also talk about, the folding of the cortex of this participant is just different. So then you might not see that. So that's something to get used to. And of course, the usual statistical tests, they pick up on this between subject variability. So if you have something happening in most of the participants, then if you do a t-test on the group level, this will usually come out significant. If you have a phenomenon of interest that varies a lot between participants, then it will come out not significant. But one should be aware of it. So because we will mainly look at, of course, at event-related potentials, how they are supposed to look. In a given data set, they might not look for each and every participant like that. Yeah? Good. So that was already the first rough and very general ride through event-related potentials. Other questions about this aspect? So general questions that you were never really clear about with EEG and that we might cover in this course or not, or which came up now. Or maybe you're just tired because the whole thing started at 8 already. No questions. Good. Then everything was clear. Yeah, I can only encourage you to do EEG studies. And maybe you will get after this course a little bit of more of a feeling why I think so. Good. So the next big part of the course is now to look, like we did for the fMRI, into the physical and biological underpinnings of this. Because in MRI, of course, everybody is amazed by the fact that this machine can make these pictures. So there's a lot of interest in the physics. With EEG, it's more like, yeah, electricity, I just plug something in, it works. So maybe there's a little bit less of interest in the physical foundations. It nevertheless pays actually to think about them or to revise or review that, and especially then also to understand the more advanced analysis types like source space analysis that you can do. And then, of course, the other question is, what do we actually measure when we put the electrode on the scalp? How much, how can we bring this into alignment with our undergraduate textbook model of action potentials and so on, and cells? So what is it that we measure? And this is the content of the second section of this course, which actually uses material from Electromagnetics with Applications by Kraus and Fleisch. This is a book that I found when I think I found it when I wanted to write the method section of my PhD in Birmingham, because I did EEG fMRI integration, so I felt like I should write something about the foundations of EEG, and I actually wanted to understand what this current density thing is that Loretta, which is a source space analysis method, gives me. So I looked at this book by Kraus and Fleisch and found what I read there helpful at that time. I'm not sure whether this is the best electromagnetics book ever written. Just don't know. I haven't read many electromagnetics books. Actually, I only looked into that one. But yeah, I found it helpful because it wasn't too long and it was on the point. But you might have other electromagnetics books which are better. So from there we take the majority of the electrical underpinnings, and then from the Principles of Neuroscience by Eric Kandel, we take some parts on the neural origins, because they have nice pictures on that, and also a nice coverage there. Again, the rules for this course and the oral exam are: you need to know what is on the slides. The references that I give you, like the two books that I passed around, or these here, you can look into them. Actually, somebody once borrowed this. And use them for further study, but you're not required to know anything that is not on the slides. Yeah, just that you know. So, electricity. Basically going back, essentially this is going back to your high school physics. And and reviews some key terms and concepts that come up throughout EEG research. Maybe the main thing that comes up once you actually do your first EEG experiment, or even if you're just a participant. Even if you're just a participant, people will put some gel into the electrodes, and then they will ask them, so what are you doing? Why are you doing this? And then they will say, yeah, we have to get the impedances down. So they use a word called impedance, and you can see the whole thing that we talk about electricity just as background to know what impedance means. Another aspect of going over these things is that you actually know what these black lines mean that you record there, at least to a certain degree. And another aspect that you can see is that if you use source space localization, so trying to figure out where the activity is coming from, then you will definitely be left to deal with current density. So yeah, so it makes sense to go over these key terms and concepts. The level is, of course, again, like in MR physics, we are not going to do a real physics course here. We're just trying to revive some concepts and revive some concepts and get some definitions into our brains, so that we have a little bit of a better feeling, but still the feeling that actually we should really read a physics book. And that's kind of the stuff here. The good thing is you don't have to read a statistics book, because I give you a statistics book. Good. So we start with very few or very basic electricity concepts. And actually this slide actually tries to motivate even more why we're looking at them than I just did. So why are we talking about electric charges? Well, because in the EEG setup, we have ions as carrier of charge in bioelectricity. And apparently when we look at that in our EEG traces, we are directly, more or less directly, look at electric charges and how they move around as ions in bioelectricity. Why do we talk about electric field? Well, because you read in basic introductions to EEG research, you read something about what is called the open field configuration of pyramidal neurons, which are these neurons that you have in a specific layer of cortex. So, yeah. And then you actually also have this great thing that you have these things called local field potentials, which is, we will come to that, which makes no sense whatsoever to call something local field potential, but you have them, and then it makes sense that you, and people talk about it, so it makes sense to dissociate between fields and potentials. Electric potentials we have to talk because they're the basic EEG time series measure, electric current density as source modeling I told you about. Electric conductivity plays a role as a basic concept for EEG forward models, which when you click them in SPM will show up, so makes sense to know about it. Impedance we talked about. So this is kind of a motivational slide to deal with these physics concepts in our context, and also should help you to relate when you learn these basic definitions always to something that you're actually interested in. At least I hope that, namely EEG. Of course, you can say, EEG I don't like, I want to do fMRI. Yeah, what can we do? Good. Some basic definitions, and these are again slides that are not eye candy to have something nice to look at in the last 20 minutes of the course today, but these are slides for you to memorize definitions so that you have the feeling that you at least know a little bit. So just like in MRI physics. So what is electric charge? Electric charge is a property of some subatomic particles, electrons and protons. Not all of them are charged, as you will remember. Neutrons are not charged. And ions, which determines the electromagnetic interactions. Electrical charge matter is influenced by and produces electromagnetic fields. That's a definition that one can live with. Electric fields, and this is only the field that we will actually talk about, is a simple field of a simple type of electromagnetic field that is produced by a non-moving electrical charge. Yeah? So we are not dealing with in physics you deal with electrical fields and also magnetic fields that happen when things are moving. So you might, if you watch some careful META, maybe I should always say when something META is happening. META, maybe you've heard, recently saw that in Nano that the North Pole, the magnetic North Pole of the Earth is wandering. So it's not at the geographical North Pole, but it's wandering, and it has been doing that, so it's nothing really novel. But this is, then the question is, where does the Earth magnetic field actually come from? And the Earth magnetic field is due to the fact that you have these, at least that's the idea, that you have this magma currents inside the Earth, and they move in certain ways, and they produce the magnetic field. And now if they change their movement, then of course the magnetic field also changes, and then of course this can lead to different magnetic field lines. This is actually important because the electromagnetic field of the Earth shields the Earth from all these charged particles that come from the sun, and if it goes away, then everything is just coming towards us, and we will all die, and cell phones will not work anymore. And of course, there you're dealing with electromagnetic and electrical fields that are dynamic. We are not interested in that. We are just looking at electric fields in the static case. Electric potential, so the basic measure that we are interested in is best defined with respect to an electric field. So this is where we have to talk about the electric field first, and is the capacity of an electric field to do work on an electric charge, and is typically measured in volts. So that it's also important that you associate the right units with the right concept. So electric potential measured in volts, and of course the basic outcome of EEG measurements are microvolts, so 10 to the power of -6 volts. Electrical current, we need that because mainly because of source reconstruction. Electrical current is, of course, as you all know, is the movement or flow of electrically charged particles, and is typically measured in ampere. Electrical resistance is the opposition to the passage of electric current through an electrical conductor. Its inverse is electrical conductance, and this refers to the ease with which an electric current passes the conductor. So resistance is fairly intuitive, so it's the resistance against movement. So these are the basic intuitive definitions of the things that we will be dealing with, and one can make this a little bit more formal to really know what one's talking about when one is talking about event-related potentials. What do we have next? So this is now going a little bit more into the details of what an electric charge is, and basically associating terms with the concept of an electric charge. So the basic electrical quantity, and that's important, so the basic electrical quantity, so the basic thing that you have in electricity is the electric charge. It's usually denoted by Q and measured in Coulomb. And then you might know from your high school physics that an electron has an electric charge of -0.6 to 10 to the power of -19 Coulomb. And an electron and a proton, they have the same charge, but with opposite signs. So protons are positive, electrons are negative. And then I guess you went all over these atomic. So who has went over the Bohr model of atoms? Bohr model? Okay, so you know all of this. Good. Then, if you have an electric charge, what is an electric field? An electric field is a vector field. Actually, I haven't told you that yet, but I will tell you again. In statistical methods, you need to revise your calculus skills, because we need your calculus skills for for the stuff that we're going to talk about in terms of random field p-value correction and also DCM. So as you've seen maybe already in the notes, there's a big chunk on calculus, which I would ask you to revise on your own. There you will also find a discussion of vector fields. Vector fields, or the term field doesn't mean much. It just means it's a mapping, so a function from a 3-dimensional or from an n-dimensional to an m-dimensional space. So it allocates a multivariate entity to every point in space in this case, but to every point in an n-dimensional space. So instead of having something mapped from an n-dimensional space to a 1-dimensional space, which would be called a multivariate real-valued thing, or from a 1-dimensional to a 1-dimensional space, which would be called a univariate real-valued thing, here we're dealing with multivariate vector-valued functions, and these are called in physics they are called fields. Fields in mathematics are something completely different, but in physics, these functions that take something multidimensional and give you back something multidimensional, as shown here, are called fields. This is why this explains that the electric field is called field, because it's a field, and it refers to a mapping. What it gives, or what an electric field is an allocation of a 3-dimensional force vector, which I call here ER, to each point in space. So physics always deals with the case of 3-dimensional things, because at least without time, the world appears 3-dimensional to humans. And then, of course, you can encode each point in space in a 3-dimensional coordinate set, like you know from school. Once you define an origin, then you can say, okay, this point in space is x this, y this, and z this. Now, what an electrical field does given by an electrical charge is that once you have an electrical charge here, this is the electrical charge, it induces everywhere around it, it induces an electrical field, meaning that now at each point around this electrical charge, you have a force vector that determines how, and we will see that, another electrical charge is moved or affected by this original electrical charge. Yeah? And the field thing is this abstraction, or this thing, I don't know how to call it differently, that assigns to each point, each 3-dimensional space, each 3-dimensional point in space, a 3-dimensional force vector that says how a different force will be moved in this direction, this direction, this direction. So field just means a multivariate vector-valued function, and in this case, the electrical field is going from 3-dimensional space to this 3-dimensional force vector. It's measured in volts per meter, why you will see, and it's defined as the force that a specific charge exerts on a unit charge. Let's look at the example, and then I'll tell you what these formulas want to say. So the basic thing here is what is the force that a second, what is called a test charge, is exposed to when there's a first charge. Yeah? So Q1, so this thing here is the first charge. It induces electrical field everywhere. And now you have a new charge. You bring it into the system, and maybe you did that actually when you were in school, that you put something into an electric field, and then this will be moved. And the way it will be moved depends on, and this is what you see here, and this is what is called Coulomb's law. This depends on how charged these particles are and whether they actually oppose each other or not. So if you have something negative and something positive, they will not oppose each other. But if you have two same charge things, they will oppose each other. Of course, in one case, the force is in this direction, the other is in this direction, so that's clear. And of course, the force that this test charge is exposed to depends on how charged these particles are. right? So that's at least the very basic old school non-quantum mechanic way, so this kind of classical mechanics way of seeing electricity, something charged, something also charged, something more charge, more force happening, something less charge, less charge happening. And then this also, of course, if the field is stationary, so it, well, let's say isotropic, if it has the same direction all over space, then it's only a question of distance. If the thing is closer to, the test charge is closer to the original charge, then of course the force will be stronger. The force is strong in you, and it will be less if the thing is further away. And this is what this little equation says, that which is called Coulomb's law, which is a fundamental thing that one can know in physics, that the force that such a second charge is exposed to depends on the charges of these two, so on the electrical charge of these two charges, and the distance, and that's about it. Now, this force normalized by the and with the force, you should always think it's a three-dimensional entity that says in which direction. This force normalized by the value of the second charge. So this is what it meant by that it's for a unit charge, unit test charge, that it exerts on a unit charge. This is why it's divided by the second charge. That is the electrical field. Yeah. So the whole thing that this whole thing doesn't say much. It says there's a first charge. The electric charge is just there. It's given by God. This charge induces a force everywhere, and this force, because we are dealing with 3D phenomena, is a three-dimensional force vector. Now we have a second charge, and we want to know how is the second charge affected by this first charge. And then it depends how charged are these charges. There's nothing I can do about this terminology, but how charged are these two charges? Well, if they are more charged, then the force will be stronger. If they're less charged, the charge will be the force will be less strong. How far are they apart? If you're closer to it, the force will be stronger. If you're further away, things weaken out. It doesn't affect that much. And the resulting force vector that is then exerted onto this test charge, that's the electrical field. I think I said the same thing now in 3 different ways. I don't know which one was the clearest. And these pictures are also more intuitive than anything. Maybe we find something else here. One thing that is also important is the medium in which this whole thing happens. So if this is happening in vacuum, where there's nothing in between, then of course things are, let's say, strongest. If there is something that is actually not conducting electrical forces well, then things will be a little bit less. So this is where these dielectric constants always come in, which you might have measured in school. Has anyone measured a dielectric constant in school? Who has measured a dielectric constant in school? I did it. I remember that. Because I never understood what I was doing there. But I remember that we looked at dielectric constants. What have you done when you did electricity in school? What's the first image that pops into your mind when you think of your electricity teaching in school? Circuits, like doing these kind of things. Yeah, I also remember that. So that we put, I never really know what I did there, actually. You had these resistance things, and then you could have a lamp, and then it was going on or not. And then we could do, didn't we do like, we will see that also, Kirchhoff's law, this thing with the resistance that if they are in parallel, this is something I think one also did with these circuits. Yeah, the teaching is not really good in school. Okay, but I think we talked about at some length now what an electrical field is. You should see that. So the way I see this whole concepts in physics is as mathematical models that the physicists ascribe meaning to and forget that these are mathematical models. These are mathematical models. An electrical field is a function that defines for each point in space a force vector. That's the electrical field. Physicists forget that this is a mathematical model and think this is reality. That's the problem of physicists. It's not our problem. For us, an electrical field is this mathematical model that tries to model the phenomenon. If you have charged things and you have them in a very controlled experimental setup, something happens that you can observe and you try to explain that with the things that you see. Okay, the charge was very close to it, or, oh, I'm doing this in some kind of jellyfish, so it's not happening much, or you do it in vacuum. Yeah? Electrical field. I think I said enough about electrical field now. Good. Questions about electrical fields? No. Good. Now, electric potentials are something different, namely they are mappings from three-dimensional space to one-dimensional space, and they actually are kind of a, if you want, a summary of electrical fields. So electrical potentials allocate to each point in space a scalar quantity. And this quantity is referred to as electric potentials at that point due to the electric field of a charge of a specific value. So you first have the electric field and then you can say what the potential is. One thing that is important with respect to electric potentials, which will also come up again when we are closer to EEG phenomena, is the superposition principle. Now, that means if you have multiple charges arranged in some kind of three-dimensional space, the effects on the potential at different points in space add up. Yeah? So that is what is called the superposition principle. This is when you have two things going on in the brain at basically the same amount but in different directions, then you will not see anything in the EEG because they cancel out due to the superposition principle. Now, the electric potential between 2 points in space is the work that you need to do to move a test charge in this setup where you have an original charge against or with the electrical field. Yeah? So the idea is first charge is there and uses electrical field. Electrical field are these forces that depend on space and the charges. Now you have your test charge, and now you put it somewhere, it experiences a force, and now you want to move it with your hand. And depending on how the charges are set up, in which kind of medium you do this, and what the sizes of the charges is, this might be a lot of work, like this, or it may be really a little work, like this. And then it depends on, of course, how far you move it, but you can normalize that to a unit, for example, a meter. And then you can allocate to each point in space a number. And now the question is, what is the reference point? And this is actually where the debates already start in terms of EEG, because ideally, if you have an electrode, you have a reference, you would want to compute the electrode, the potential, with respect to this reference point. It means you need an electrical neutral point somewhere in space, but you don't have it. And then certain people have different ideas for this basic idea of what the electric potential is. If it's just a number that you have in space, it refers to moving the charge from infinity to there, or the other way around, depending on the sign. Yeah? So that you don't have to, if you think about, you have these three-dimensional forces everywhere in space, and now a potential is refers to this movement. Then of course the question is, where does the movement start and where does it end? And of course you can compute that with respect to whatever you want. So you can, of course, have like a point in 3D space here and another space in here, and then you can compute the electrical potential from moving from here to here, from here to here, and to here to here. But you can also just, if you want an absolute potential, then you of course have to take this idealized idea of infinity from where you move an electrical charge in the presence of this original charge. And introducing infinity is always a good point to end a session. So because we're a little bit late, I will stop here and we will start again with electric potential. You can also read up a little bit on this and get a little bit more into the spirit of dealing with basic concepts in electricity for these first 2 sessions of the course. Good. Any questions? General scan stuff, thingy, projects? No. Good. Then see you later today at your seminar today, because you invited the speaker, and have a good start of the term and get to work.